Okay, so in this video we're going to complete our analysis of the Gaussian mixture model by finishing the M step, the maximisation step. So in the previous video we calculated what this thing is, the expected ZnK. And now what we need to do to update our parameter estimates is we need to maximise this thing, this expected log likelihood, with respect to the parameters in our model, which are the means, covariance matrices and mixture proportions. Now that we've already calculated this, we can just treat this expected ZnK as a constant in the following analysis. So the first thing we're going to do is we're going to maximize this with respect to the vector mu k, the kth mean. So we're going to take the derivative of this with respect to the vector mu k. We're going to set it equal to 0 to find out what our new best guess of mu should be. So if we take the derivative of this expression with respect to mu k, this is just a constant. This is not a function of mu k, so that will just go to 0. So we're going to end up with the derivative of this log likelihood here. Sorry, this log Gaussian. Okay. So what I'm going to do is I'm going to write down what we want is the derivative with respect to the vector mu k of log normal distribution or Gaussian distribution with xn as the argument and then mu k as the mean, sigma k is the covariance matrix. And I'm going to just keep in all the terms that are a function of mu k, because everything else will come outside of this as an additional constant. That's going to disappear when we take the derivative anyway. Okay, so if you only keep the things that are a function of mu k in here, what you end up with is this stuff that you'd see normally with the Gaussian. So we're going to end up with this half. We're going to have an xn minus mu k transposed multiplied by the inverse covariance matrix multiplied by xn minus mu k. And like I said, plus some other stuff which doesn't depend on mu k. And then if you multiply all this stuff out, kind of one by one, you end up with this minus a half again, multiplied by what you end up with is there's a mu k transposed times covariance matrix minus 1 mu k. So that's come from this multiplied by this multiplied by this. And then there's also two terms that are equal to xn transposed your covariance matrix inverted times mu k. Again, plus some other constants that we're not too worried about. And we're performing vector calculus here, so there's a few relations that we need to know that we won't prove here. We'll just kind of accept them. So one of them is to compute this thing. If you have, let's say we have a vector x transposed multiplied by a matrix A multiplied by another vector x, we take the derivative with respect to the vector x, what you end up with is A transposed plus A times that vector x. So that's the first relation we're going to use, and we're going to use it to evaluate this thing. So we notice that this is a covariance matrix, and it's symmetrical, so its transpose is equal to the original matrix. So this covariance matrix, even the inverse covariance matrix transposed plus covariance matrix, you just get two of the same thing. So using that relation we just wrote in red, we know that this can be written as, so we still have our minus a half, we can have 2 times that covariance matrix. And this, like I say, we've got this vector left over at the end, which is mu k. Okay, so that's the first bit done. Then we've got a minus what's the next part? Okay, so the next thing we're going to say, and we're not going to prove it, we're just going to kind of state it. If you have a vector transposed, let's say multiplied by another vector x, and you differentiate that with respect to x, what you end up with is that vector. Okay? So let's see, what have we got here? Well, this stuff, this is a vector transpose multiplied by this covariance matrix. That can be treated just as a single vector transposed. So it's very similar to this A here. So we know that from that relation, what we're going to need is that this will become equal to -2, just because it's a constant, and then the transpose of this thing. Remember, the transpose of our inverse covariance matrix is equal to the original inverse covariance matrix. So original covariance matrix inverted multiplied by xn. Okay, great. And obviously this half, so there's a minus there, which I forgot. So then we can multiply through that, through all this stuff. And so we're going to get sigma k to the -1 times xn minus sigma k to the -1 times mu k. Okay. So we're going to substitute it all into this and set it equal to 0. So that means that the differential with respect to mu k of this thing is going to be equal to, so we're summing over k's here, but when we take the differential with respect to one of them, they'll all, every term in this summation will disappear except for the one we're interested in. It's going to become equal to the sum over n equals 1 to n of our expected znk, which we're just treating that as a constant. And then it's the derivative of this with respect to mu k, so that is equal to what we have here. Okay, fine. And then we're going to set that equal to 0 to find if we're going to find our optimum mu k, that's going to be equal to 0. Remember that our optimum mu k is going to be that's the value we use in the next iteration of the algorithm. Okay, so now if we just keep going with this, what we have is that we can pre-multiply. So this is a vector 0, so I'll try and make it look a bit more bold. This is a vector of zeros. We can pre-multiply by sigma k, both sides. So what we end up with is that the summation over n of our expected znk multiplied by xn, and if I just move this across, that's equal to our summation over n equals 1 to n expected znk multiplied by mu k. So I should say that equation implies this one rather than is equal to. And then we just rearrange this to find that our next mu k should be equal to, simply, we have a numerator, and then we have a denominator, which is equal to this. Okay, and just to avoid confusion between the ends up here and the ends down here, what we'll do is we'll call this an n dash. So it's a summation over z n dash k. And so there we go. We've got our new best estimate for mu k, and it's equal to this thing here. So what I'm going to do is, now that we've done that, I'll delete this stuff. Replace the bits I accidentally deleted. I'm going to place that, let's say, up here. So that thing is the first part of our m step. So in the next two parts, we need to find the our next best guess at sigma k and pi k. Okay, so now we need to take the derivative of this with respect to our kth covariance matrix, and this is the only term that depends on the kth covariance matrix, so we'll expand this. And in the following, it's easier to work with the precision matrix rather than the covariance matrix. So I'm going to define, let's say, a k has been equal to the kth precision matrix, so it's sigma to the -1. So expanding this term, we now have to include the normalizing constant for the Gaussian. So that is half, then we have the log determinant of our kth precision matrix, minus a half. Then we have xn minus mu k transposed, multiplied by our kth precision matrix, again multiplied by xn minus mu k. And that is equal to, so we'll just take the half outside. So we have a log determinant precision matrix. Then there's a trick here which is going to make our vector calculus a bit easier. So this is equal to minus, you can write this as the trace of our matrix K, the precision matrix, times by we have xn minus mu k multiplied by xn minus mu k transposed. So what we have here is our precision matrix. You can show that if you multiply that by this thing, which is now a matrix itself, and then you take the transpose, then you end up with this term here. Okay, so now we have two properties rather that we're going to rely on here. So I'll write them over here. So what we want to do is we're going to find the derivative with respect to AK, precision matrix, kth precision matrix of this stuff. So the first property we're going to rely on, which again I'm just going to state, and we won't prove it here. So if you have some matrix, let's say we have the log determinant of some matrix A, we take the derivative of that with respect to matrix A, then what we get is that matrix inverted, transposed. So we're going to use that to tackle this part here. And we also have the property that if we have the trace of some matrix A multiplied by another matrix B, and we take the derivative of that with respect to A, then what we're left with is B transposed. So you can see we're going to take the derivative of log determinant kth precision matrix. So we're going to end up with the inverse of A, which in this case is our covariance matrix, and it's transposed, but the covariance matrix and its inverse are symmetrical. So transpose is the same as the original matrix. So this is equal to, so we still have our half. And then, like I say, we're just going to have the inverse of this, which in our case is actually sigma k. And then we have a minus. So if we look at this relation here, this thing is a matrix, so we can treat that as being like B. So that means that we take the derivative of this with respect to matrix AK, we end up with this thing transposed. So we end up with xn minus mu k transposed multiplied by xn minus mu k. Okay. So now we're going to substitute that back into here. So we've got, so I'll just copy this. Okay. So what we've done is we've taken the derivative of this with respect to, well, in this case it was actually the precision matrix, which is equal to, so summation over n multiplied by our expected znk, which are all constants. This term's going to disappear. And what we've actually got is all this stuff. Okay, so in fact we can remove here, remove all this. And I will write the half that's here. There. And then we'll copy this straight in. Okay, and then we're going to set that equal to 0. So we can find out what our next best guess at the covariance matrix, kth covariance matrix is going to be. Okay, that's a vector. Matrix, sorry. So now this half is going to disappear on the other side. So this all implies that. So we've got all this stuff. So we've got our summation over z's multiplied by this kth covariance matrix is now going to be equal to, so we multiply this term by our summation over z's, and we move it over, or rather this is summed over n, so it becomes equal to summation over n equals 1 to n. So because we still have n's in here, we have an expected z nk, and then multiplied by all this stuff. And now we're just going to divide by this summation. So therefore, our next sigma k, our next best guess, is going to be equal to this divided by, and again, just to avoid confusion, we'll say the summation over n dash from 1 to n with our expected value of z n dash k. Okay, so that's what our expected, that's what our next best guess at the kth covariance matrix is going to be. So again, I'm going to delete all the stuff we used to get there. So we'll get rid of that, get rid of that. We don't need this anymore. All this. And I'm going to move this up to here. Okay, so what we have now is our expression for the for our next best guess at the covariance matrix, and you can see both of these, they look like our standard expressions for the sample mean and sample covariance matrix, but they've kind of been weighted by the expected value that each data point has come from a particular Gaussian. So we just have one thing left to do. So we need to find our next best guess at the mixture proportions. So now we find the derivative of this with respect to pi k. So the terms in here that are a function of pi k, if we isolate those, then what we get is the summation over n equals 1 to n. We have our expected z nk multiplied by log pi k. Okay, this is slightly different because we want to minimize this, but we have to remember that it's subject to a constraint. So in the previous videos, we said that we know if we sum over all of our pi k's, that would be equal to 1. So we're actually doing some constrained optimization in this case. When we do constrained optimization, it's often a good idea to try and use something called Lagrange Multipliers. So, stated briefly, let's say we want to find the x that minimizes f of x, but it's subject to some kind of constraint, which we usually write as g of x is equal to 0. And what we do is we write down something called, we'll just call it an L, it's equal to our f of x, let's say minus a constant, it's lambda, called a Lagrange multiplier, times by g of x. Then we find the x that minimizes this. So again, we won't go on to prove that in this particular video. So in this case, we want to minimize this term, but it's subject to the constraint here. So we can also say that we can view that as subject to the constraint that the summation over k of pi k minus 1 is equal to 0. So that it looks like this constraint here. So we're going to write this down as being the thing we want to minimize minus our Lagrange multiplier. I'm going to move this down here so we have a bit more room. Times by our constraint, which is the summation over k of pi k minus 1 is equal to 0. So this is what we're going to try and minimize now. So we're going to take the derivative of this with respect to pi k. And that is equal to, so we still have this summation over Zn, expecting Zn. We have the derivative of a logarithm, so we end up with a 1 divided by pi k minus, all of these are going to be equal to 0 except for one of them that will be equal to 1 when we take the derivative. So we just end up with a lambda there, which is the Lagrange multiplier, which is a constant, and we need to find it. So now we're going to set this equal to 0 because this is the thing that we're trying to find the zero derivative of. Okay, trying to maximize. So now we need to find out what our Lagrange multiplier is. Well, we know that this implies that we have our summation over z's is equal to pi multiplied by pi k. Then we still have this constraint. If you sum over all k's, if you sum these over all k's, that will be equal to 1. So we're going to sum both sides over all the k's. So now we introduce this summation over k equals 1 to capital K of expected Znk will be equal to, and then the summation of this over k is just equal to 1. So it's just equal to lambda. And then we know that this is equal to 1 by definition. And then we sum that 1 n times. So it ends up being equal to n on this left-hand side. So this implies that lambda is equal to n. Okay, so now we can plug that into here. So now if lambda is equal to n, we can just write that. And so after some rearranging, this implies that pi k is going to be equal to this term, the summation of our expected z's over n, all divided by n. And so there we have it. There we have the final term for our maximization step. So again, I'll remove the stuff we no longer need. And I'll put this here. Okay, and that's it. So in fact, we no longer need this either, because we have our complete algorithm. So the ith iteration, what we do, so this is M is here, sorry, E, the expectation, E is here, and the maximization is here. So we come in with our ith estimate of the parameters of these means, covariance matrices and mixture proportions. In our E step, we calculate this expected ZNK, then we hold that fixed. And then the next iteration, we update our parameter estimates. You'll see that this term for our next best guess at the covariance matrix actually contains mu. So the thing to do is we update mu first. So what we'll do is we'll say that mu k I plus 1 is equal to all this stuff here. And then our sigma k I plus 1 will be equal to all this. But now we're going to use our current best guess at mu. So this is our I plus 1. And then finally, our I plus 1 estimate of pi k is here. And so that is our algorithm, our E step. When we have our ith guess at the parameters, we calculate this over all znks. And then in our M step, over all k's, we get our new parameters. And as we saw earlier, we know that the parameters in our I plus 1th iteration will be higher likelihood values than in our ith iteration. So now we've got all the maths for the basic algorithm, we can look at some example code. So the code is hosted on GitHub. So you need to download Git to get hold of it. I'm sure many of you have already, but if you haven't, Git's a really useful tool for collaborating with other people, writing code, and it's free. So I'm going to copy this link, which will be at the bottom of the video as well. I'm going to open Git, we'll type git clone and then the link, and that will give us all of our code. So here it is. It's all written in Python. We'll open up Gaussian mixed model examples. So here's our code. So in this part we load some data. Here we specify our initial guesses at the means, covariance matrices and mixture proportions. We then create a Gaussian mixed model object where we specify how many Gaussians we're looking for. So in this case we're looking for 3 clusters. And then we train the algorithm, we run the EM algorithm. So here NI specifies the number of iterations of EM that we're going to go through. So let's say I'll just change that to 15. It will then print some results and then plot some pictures. So I'll just run this. And hopefully when it gets to the end, it does some pictures for us. So there we go. So the red dots are our data, and it's decided that to put a Gaussian here, a Gaussian here, and a Gaussian here. So the means of those Gaussians are reported in the results. Mean 1, mean 2, mean 3. Likewise, all the covariance matrices, and then you can see that the mixture proportions are there as well. Okay, and then the actual code itself, the actual Gaussian mixed model itself is in GMM.py. So this is like a Gaussian mixed model object. So when it's initiated, this thing runs automatically. Then it has 3 methods associated with it. So it has this expectation step, where essentially we find the expected Zs. And then this maximization step, where we find the maximum likelihood mixture proportions and means and covariance matrices. And then we tell it to train for ni iterations, and it simply loops over the expectation and maximisation steps. Okay, if you'd like to use this code or build on it for anything, then it'd be good if you could create a fork on GitHub. You don't have to. I'm just kind of curious to see if this code gets used for anything and what it might turn into. Okay, thank you very much.